Intro to AVL Trees. Now, before we can discuss AVL trees, there are two important vocabulary words that we must first explore. The first one being height. How do I find the height of a binary search tree? Well, the height of a binary search tree is simply the number of nodes in the longest path from the root to a leaf node. For example, suppose this is my binary search tree. It contains just one node. Well, in this case, the root is a leaf. So the path from the root to the leaf simply contains one node. So the height for this tree would simply be 1. Now suppose this were my tree. In this case, there's only one path to look at, and that path consists of 2 nodes. So the height of this tree would be 2. Now suppose this were my tree. In this case, we got 2 paths to consider. Both paths contain only 2 nodes. So regardless of which path you consider, the height for this tree would still just be 2. Now suppose this were my tree. Once again, we have 2 paths to consider. The path on the right side has just 2 nodes, whereas the path on the left has 3 nodes. And like we said in the definition, the height is the number of nodes in the longest path from the root to a leaf. So in this case, the height would be 3. The next word we need to explore is balanced. How do I determine if a node in a binary search tree is balanced? Well, that node is balanced when the height of its left and right subtrees differ by no more than 1. For example, suppose this is my tree, and I want to determine if the root of this tree is balanced or not. To do that, I'll need to compute the height of the left and right subtrees and compare them. So, for the left subtree, there's only one node in it, so the height for my left subtree is just 1. On the right side, once again, only one node, so the height is just 1, giving me a height difference of 0. So this tree, balanced. Now suppose this is my tree, and once again, I want to determine if the root is balanced or not. Well, in this case, the height of the left subtree is 2, while the height of the right subtree is 1, giving me a height difference of just 1. So once again, this tree is balanced. Now suppose this were my tree, and I want to determine if the root is balanced or not. In this case, the height of the left subtree is 3, while the height of the right subtree is 1, giving me a height difference of 2, which obviously is greater than 1. So in this case, the tree is unbalanced. Then let's say I add another node to the right side, and I want to determine if the root node is balanced or not. In this case, the height of the left subtree is still 3, but the height of the right subtree is now 2, giving me a height difference of just 1, making this tree balanced. Now, why do I care whether or not a tree is balanced? Well, to illustrate why it makes a difference, suppose these are my 2 trees. Both have 7 nodes, both contain the same exact values. However, one is completely balanced, while the other one is completely unbalanced. Suppose I want to find the number 35 in these 2 trees. Well, as you know, all searches start at the root. Then I compare the number I'm looking for to the root value. In both cases, 35 is greater, so I go to the right. Once again, in both cases, 35 is greater, so I go to the right. I compare again. In the case of the balanced search tree, we've found a number, we're finished. On the right side, however, we're not done. 35 is greater than 15, so we keep going. Once again, 35 is greater, so we go to the right again. 35 is greater, go to the right. 35 is greater, go to the right, until we finally find 35 in the right binary search tree. So, as you can see from this example, clearly the maximum number of comparisons one may make during a search correlates to the height of the tree. However, based on this example alone, it might not seem like that big of a deal, right? Because again, in both cases, both trees had 7 nodes. The height of the balanced tree was 3, and the height of the unbalanced tree was 7. So in this case, the difference in the number of maximum comparisons is just 4. And when you consider how fast computers operate, 4 comparisons really is not a big deal at all. But Now suppose our tree contained 1,000 nodes. Now my screen isn't large enough for me to depict a tree with 1,000 nodes, so I'll just go ahead and give it to you. The height of a completely balanced tree with 1,000 nodes would be 10, whereas the height of a completely unbalanced tree storing 1,000 nodes would be 1,000, meaning the difference in the maximum number of comparisons is 990. And let me reiterate, this difference, it's not because the second tree stores way more data than the other one. That would actually make logical sense. For a tree, if it stores more data, obviously it'll take longer. But that's not what we're comparing. We're comparing two trees that store the exact same amount of data. However, one is balanced, and the other is completely unbalanced, leading to a difference of almost 1,000 comparisons. And now let's extrapolate that to 1,000,000 nodes. A completely balanced tree storing 1,000,000 nodes would still just have a height of 20, whereas a completely unbalanced tree storing 1,000,000 nodes has a height of 1,000,000, giving us a height difference of almost 1,000,000 comparisons. And once again, we're talking about two trees that store the exact same amount of data, with one taking much, much longer than the other. So clearly, as the number of nodes increases, the height difference between a balanced version of that data and an unbalanced version of that data becomes more and more significant, making a tree that's able to keep itself balanced at all times increasingly more valuable. Which brings us to the definition of an AVL tree. An AVL tree is a binary search tree that is always balanced. How an AVL tree is able to keep itself balanced at all times, we will discuss in the next video.